Advanced semiconductor manufacturing depends on a highly consolidated chemical bottleneck. 4 Japanese firms control 92% of the global extreme ultraviolet photoresist market. JSR Corporation alone commands 39%, generating $450 million in annual revenue. Qualifying an alternative chemical supplier requires 18 to 24 months of testing. The physical constraints of sub-7 nanometer lithography dictate these extreme market dynamics. As silicon features shrink, allowable metallic impurities have dropped 100-fold, from 1,000 parts per trillion down to 10 parts per trillion. At the 3 nanometer node, a single metallic particle at 10 parts per trillion causes catastrophic bridge defects. Achieving this level of purity requires specialized cryogenic distillation and fluoropolymer-lined vessels. This level of concentration has historically triggered systemic industrial failures. In July 1993, an explosion at a single Sumitomo chemical plant in Japan instantly eliminated 60% of the global supply of ultrapure epoxy resin. Global memory chip prices surged by over 50% within 60 days. A single physical disruption at a modern Japanese monomer facility would immediately halt advanced global logic fabrication. The global transition to high-temperature energy systems and advanced defense manufacturing has triggered a structural deficit in molybdenum. Annual demand is projected to reach 290,000 metric tons by 2030. This expansion is driven by a 6.2% compound annual growth rate in high-strength, low-alloy steel production. The resulting supply deficit will peak at 15,000 metric tons in 2027. In response, molybdenum oxide spot prices have surged 42%, rising from $18.50 to over $32 per pound. This price volatility reflects a market unable to rapidly scale production to meet critical infrastructure needs. Molybdenum supply is structurally inelastic because 58.3% of global output is recovered as a secondary byproduct of copper mining. Production volumes are dictated by copper market dynamics rather than direct steel demand. Geographic concentration compounds this vulnerability. China controls 45% of global supply, representing 117,000 metric tons, and dominates primary mining. Meanwhile, declining copper ore grades in South America have reduced Chilean byproduct yields by 8.4% from 2021 to 2023. This leaves Western defense and energy supply chains highly exposed to single-point disruptions in East Asia and South America. Modern gas turbines operate at temperatures exceeding 1,600 degrees Celsius, surpassing the melting point of their nickel-based superalloy blades. To survive, these blades require intricate internal cooling passages formed during casting by high-precision ceramic cores. As cooling geometries advance to double-walled architectures, physical manufacturing yields collapse. Generation 4 ultra-complex cores exhibit a sintering yield of just 40%, driven by high-temperature dimensional warping. This warping frequently exceeds the strict tolerance threshold of plus or minus 0.05 millimeters. Consequently, scrap rates have escalated to 60%, multiplying processing costs per net good casting. This physical limitation represents a critical barrier to increasing turbine thermodynamic efficiency. This yield collapse has created a severe macroeconomic supply-demand divergence. Global demand for high-precision ceramic cores is projected to reach 6.5 million units by 2026. Conversely, production capacity is highly inelastic, growing at a compound annual rate of just 1.5%. This slow growth stems from extreme capital costs and specialized tooling lead times. The resulting structural deficit will expand to 2 million units by 2026. This represents a 30.7% supply shortfall, directly capping global single-crystal blade casting volumes. Because the market is dominated by only 2 primary suppliers, this bottleneck cannot be easily bypassed by capital injection alone. The upstream material bottleneck now dictates downstream aerospace and defense realities. Procurement lead times for ceramic cores have surged from 12 weeks in 2019 to 52 weeks in 2024. Over the same period, the average unit cost of these cores has risen from $450 to $1,150. This price escalation reflects yield loss pricing and raw material surcharges. Consequently, commercial and military engine delivery backlogs have extended from 14 months to 44 months. The pace of global aviation and power infrastructure deployment is physically tethered to ceramic sintering cycles. Without fundamental material science breakthroughs in core binders and sintering control, this industrial friction will persist. The rapid expansion of low Earth orbit satellite constellations has transformed noble gases into critical strategic assets. Xenon and Krypton serve as the primary reaction mass for high-efficiency electric propulsion systems. Because these gases exist only in trace atmospheric concentrations, their recovery is entirely dependent on cryogenic air separation units integrated into large-scale steel mills. This structural coupling makes the global supply of satellite propellants highly inelastic. Global xenon production is capped at approximately 12.5 million liters annually. Meanwhile, space sector demand has scaled from under 4% of global supply in 2018 to a projected 40% by 2026. This rapid demand growth has created a structural supply deficit. Geopolitical disruptions in 2022 sidelined major Ukrainian purification facilities, causing spot prices to spike from $15 to $120 per liter. Geographic concentration of crude noble gas extraction mirrors the footprint of global heavy industry. China controls 35% of crude extraction and 45% of high-purity purification, leveraging its massive domestic steel manufacturing base. Prior to 2022, Ukraine purified up to 50% of the world's high-purity noble gases. The conflict in Ukraine permanently shifted these purification nodes to East Asia and the United States. The United States remains highly vulnerable to supply chain shocks. It possesses only 5% of global crude extraction capacity and 10% of advanced purification infrastructure. This domestic deficit forces Western aerospace firms to rely on volatile foreign supply chains for critical defense and commercial satellite launches. Any disruption at East Asian processing facilities immediately threatens domestic orbital deployment schedules. To bypass the physical supply limits of xenon, satellite operators are forcing engineering and thermodynamic trade-offs. Krypton offers a 90% reduction in raw material cost, priced at $4.50 per liter compared to $45 per liter for xenon. This economic incentive has driven mega-constellation operators to transition to Krypton-based thrusters. However, this transition imposes severe physical penalties. Krypton requires 15.3% higher ionization energy, measuring 13.99 electron volts compared to 12.13 for xenon. Its lower atomic mass and storage density demand larger propellant tanks and higher onboard power allocation to achieve comparable thrust. Argon represents the absolute thermodynamic floor at 10 cents per liter, but its extreme ionization energy of 15.76 electron volts restricts its use to ultra-high power deep space propulsion. The limits of orbital logistics are ultimately governed by these fundamental chemical and economic realities. Enhanced geothermal systems require drilling into deep crystalline basement rock, where temperatures exceed 250 to 350 degrees Celsius. At these thermal thresholds, standard silicon-based downhole electronics fail due to thermal carrier generation. Bulk silicon semiconductors experience junction leakage and thermal runaway above 150 degrees, dropping operational lifespan to under 5 hours. Silicon-on insulator technology extends this limit to 225 degrees, but decays exponentially at 300 degrees. Wide bandgap silicon carbide microelectronics maintain 5,000 hours of operation at 300 degrees, but face severe supply chain constraints and low wafer yields. This material bottleneck restricts real-time telemetry and directional drilling in deep geothermal reservoirs. Thermal degradation is not limited to electronics. Downhole sealing systems face immediate mechanical failure under extreme thermal stress. Standard nitrile seals, the baseline for conventional oil and gas wells, degrade within 2 hours at 250 degrees Celsius. This degradation causes rapid pressure loss in mud motors, forcing operators to pull the entire drill string. High-performance perfluoroelastomer seals extend operations to 150 hours at 250 degrees, but their lifespan drops by 88% at 300 degrees. Experimental fluoropolymers can withstand 96 hours at 300 degrees, but increase sealing system costs by over 400%. These material limitations dictate the exponential cost curves of deep crustal drilling. Drilling through hard crystalline granite to 6,000 meters costs $15,000 per meter, compared to just $1,050 in conventional sedimentary basins. This economic trajectory mirrors Project Mohole, the 1961 deep ocean drilling attempt that collapsed due to rapid tool failure in basalt. Today, non-productive time, spent replacing failed electronics and seals accounts for 45 to 60% of total deep geothermal well expenditures. Tripping a drill string at 5,000 meters takes days and costs hundreds of thousands of dollars per incident. Until wide bandgap semiconductors and advanced elastomers scale, the thermal limits of materials will remain the primary barrier to baseload geothermal energy. Pressurized heavy water reactors bypass the geopolitical bottlenecks of uranium enrichment by utilizing natural uranium. This operational independence shifts supply chain vulnerability entirely to the chemical synthesis of deuterium oxide. The global heavy water market has entered a structural deficit. Active global production capacity is stagnant at 300 metric tons per year. This flat supply curve collides with a massive wave of reactor refurbishments. Demand is projected to peak at 1,600 metric tons in 2027. Canada eliminated 700 metric tons of annual domestic capacity when it decommissioned the Bruce facility in 1997. Consequently, Western operators rely on finite stockpiles, while India controls over 75% of active global capacity. Synthesizing reactor-grade heavy water is governed by severe thermodynamic constraints. Natural deuterium abundance is only 150 parts per million. Extracting 1 metric ton of 99.8% pure heavy water requires processing 340,000 metric tons of feed water. This low concentration makes the extraction process highly energy-intensive. The dominant Girdler sulfide process requires 6.1 megawatt-hours of total energy per kilogram of product. This high energy intensity exposes production economics directly to regional thermal energy price shocks. Furthermore, the process relies on highly corrosive hydrogen sulfide gas at 2 megapascals of pressure. These chemical hazards require specialized nickel alloy piping and strict safety exclusion zones, preventing rapid capacity expansion. Physical design of pressurized heavy water reactors dictates their massive material inventory requirements. These systems require approximately 0.8 to 0.9 metric tons of heavy water per megawatt of electrical capacity. Major life extension programs in Canada and Romania require 5,800 metric tons of high-purity coolant by 2035. This concentrated demand spike exhausts existing Western reserves. Systemic risk is compounded by chronic operational losses. Normal plant operations experience vapor leakage of 0.5 to 1.0% of inventory annually. This leakage generates a continuous, non-discretionary global makeup demand of up to 220 metric tons per year. With production concentrated in a few national programs, the Western nuclear fleet faces a persistent operational bottleneck. Advanced telecommunications and high-power lasers depend on single crystal oxides. Growing these crystals requires melting raw materials at temperatures exceeding 1,400 degrees Celsius. This process relies entirely on iridium crucibles due to their extreme thermal resistance. However, global iridium supply is highly inelastic because it is recovered only as a minor byproduct of platinum mining. This rigid supply has collided with a massive clean energy demand shock. Iridium demand for proton exchange membrane electrolyzers grew from 200 kilograms in 2018 to 2,400 kilograms in 2024. This rapid expansion directly cannibalized the allocation available for electronics crucibles. Consequently, average spot prices surged from $1,280 to $4,800 per troy ounce. Crystal growers cannot easily substitute iridium with alternative metals. Refractory metals like tungsten and molybdenum melt at high temperatures, but oxidize catastrophically above 500 degrees Celsius. This makes them useless in the oxygen-rich atmospheres required to prevent melt dissociation. Platinum and rhodium either melt too low or contaminate the crystal melt through severe volatilization. This leaves iridium as the sole viable material for high-temperature oxide growth. A standard 150 mm crucible requires 10 kilograms of high-purity iridium. At 2024 prices, this represents an upfront capital cost of over $1,500,000 per station. Furthermore, these crucibles degrade via chemical sublimation, losing up to 0.3% of their mass per run. This degradation forces operators into frequent, highly expensive chemical refining and recasting cycles. This critical material bottleneck is highly concentrated geographically. South Africa controls 83% of global iridium mine production. This concentrates systemic risk within a single region exposed to electrical grid instability and labor disputes. A disruption at the Bushveld igneous complex immediately halts the downstream supply chain. Refining capacity is similarly consolidated. European and South African refiners control 84% of high-purity output. This means environmental regulatory shifts or trade restrictions in just 2 jurisdictions can freeze the supply of 99.99% pure iridium. The physical supply chain for next-generation telecommunications and power electronics remains tethered to this single, fragile processing node. Global maritime trade is consolidating into ultra-large container vessels. The Port of Shanghai's Yangshan Phase 4 terminal represents the frontier of this consolidation. Annual throughput has expanded from 2.01 million TEUs in 2018 to an estimated 7.1 million TEUs in 2024, driven by scaling vessel capacities. Average container vessel capacity calling at Phase 4 has scaled from 14,500 TEUs to 24,200 TEUs, forcing key cranes to reach 24 rows across. Net crane productivity peaked in 2021 at 29.4 moves per hour, but has since declined to 27.2 moves per hour. The primary bottleneck has shifted from physical crane speed to real-time computational coordination. The operational integrity of Yangshan Phase 4 depends entirely on its terminal operating system. This software must dynamically route over 130 automated guided vehicles in real time. A latency spike of just 50 milliseconds in the central routing algorithm reduces vehicle utilization to 74.1%. This 50-millisecond delay causes an immediate 12.3% drop in system-wide throughput. Backlog recovery timescale nonlinearly, meaning a 50-millisecond latency event sustained for 4 hours requires 72 hours of continuous operations to clear. At 70 milliseconds of latency, sensor polling timeouts cause vehicle deadlocks to surge by 400%, forcing manual intervention. Deconstructing the container cycle time reveals the trade-offs of terminal automation. Automated systems excel at discrete mechanical tasks, reducing total container cycle times by 31.2% compared to manual operations. This efficiency is primarily driven by a 56.3% reduction in yard-to-gate processing. Automated vehicle transit times are 16.7% slower than manual truck movements due to conservative collision avoidance and path routing deconfliction. The physical bottleneck has shifted from crane hoist speeds to the spatial coordination of the automated stacking yard, where laser scanning slew times limit peak throughput. Modern logistics bottlenecks are no longer defined by physical labor, but by the microsecond-level latency of distributed control software.